So first, we do the sound check. I hope you can hear me. I hope I can hear if someone wants to ask a question or something. I think in case someone would need to come closer and wave, I can still see a little picture of you guys. So in case, let me know. So I'm very happy to be here today. I'm very sorry I can't be there in person. As you might know, Photonics West is starting soon, and I'm already flying out tomorrow. And unfortunately, flying via Boston was not really an option. So I hope I can entertain you a little bit tonight, virtually. And of course, if you ever visit Rochester, let me know. And it's a great place to be, as you might know. And I show you around and let you know what we do in detail once you're there. So today I want to give you a little bit of an insight. I decided to name this talk Beyond the Beam, the Potential of Light Structure. As you've heard, I work with what is called structured light. And I hope at the end of the talk, you are equally excited as I am about structured light and want to learn more and want to experience all the cool properties these fields have and what they are good for. But before I start, you already heard a little bit about where I come from. I like to start with the acknowledgement usually. As we all know, in the end, there's always very little time, and I don't want to rush it. So, as you might recognize from some of the pictures, I think Stanford you already heard, but I actually did my PhD and also some postdoctoral time at the University of Münster in Germany with Cornelia Denz before I also spent some time at Wits University in South Africa with Andrew Forbes. Both of those were my PhD advisors, and I still work with both of them very closely. And in Stanford, I worked with Mark Brongesma, but also with Jelena Vukovic a lot. And today at the end, I'm going to show you one of those projects we worked on. And now, as you heard, I moved to Winter Wonderland, as I like to call it, because it always looks very beautiful when there's a lot of snow. It's a big contrast to California, but it brought me a little bit closer back to the roots to Germany. We don't have as much snow, not as beautiful winters necessarily. So I enjoy that a lot, and especially our dog enjoys it a lot. So people who have dogs, I think you might know how excited they get once they touch the snow. So beautiful place to be, even in winter. Our airport is very well maintained, so if you want to visit in winter, you should definitely take a chance. So now let's dive into the topic. I said in the beginning, I work with what is called structured light fields, and that can be various different things. I like to pull up this slide because here we have some visualizations of what actually is structured light. We can start very easy and say that if we look at colorful pictures, what we actually have is a spatial variation of, for example, the wavelength or the frequency of light spatially resolved. So in different areas in space, we see different wavelengths. Another property of light which can spatially vary is the polarization. This is what this picture up here indicates. We have the sun and we have scattering of the sun in the blue daylight sky. This actually causes the sunlight to be polarized differently, and it creates a polarization structure in the sky which actually carries the information about the sun. So this sounds interesting, I would say, at least from an optics perspective, but it's actually a quite useful tool. Maybe not for us because our eyes are kind of insensitive to polarization, mostly, not completely. But insects, for example, they can see polarization, some of them, and they use it as a means of orientation. So it's like the GPS for bees and other insects. So here we have, let's say, the information about the location of the sun encoded in the spatial structure of polarization. Another property of light which can spatially vary is the phase of light. So if we think about the bright caustic lines we see at the bottom of shallow water or at the bottom of a pool, these are actually formed if we have refraction at the water surface, we have different propagation path lengths. This means we have different phase values meeting at the bottom, causing constructive and destructive interference. So in the end, this means that we see these bright, beautiful patterns, but they actually carry information about the water surface, as well as things as the refractive index and many other things. So again, the spatial structure we have here carries some information for us. Now we can also go to much smaller scales, and this is what we see in the bottom right. If we think, for example, about a dipolar scattera or an emitter, which could be a single molecule, fluorescence, What we have here is we get also a pattern of light. Here we have the radiation pattern we can see, and the light is oscillating not only in the transverse plane, it actually has a three-dimensional polarization oscillation, which means that this oscillation of polarization can actually, again, carry information for us. In this case, it carries information about the orientation of a dipolar scattering. So now all of these can be temporally stable, but obviously we can also have a temporal variation of all these different properties. And again, this can carry some more information for us. So we have a lot of different things we can encode in light or have encoded in light. And this we know for quite a long time, but actually taking advantage of that is still very much in its infancy. So if we look at that in microscopy, we use, for example, the phase and polarization quite often to extract some extra information from some kind of optical seams. So if we think about cells, which are almost transparent, they are very not well, let's say not very well visible if we just use bright light microscopy. So what we do there is we use the phase changes of light as it propagates through the medium and translate this into something we can work with. In this case, we translate it into contrast changes. And we can do that by using something like an annular shaped aperture. And we have a phase shifting ring in the back of our microscope, which then constructs a new image for us, which shows pretty much phase variations as contrast changes, and we can see our objects much better than before. Another property of light which is changed in different media is the polarization. So if we think about polarized light microscopy, we translate any kind of polarization variations which light experiences as it propagates through media, and we translate it into something which can be color changes, or it can just be contrast changes. Again, this gives us some extra information just by adding some polarizers in our optical system, and we can learn about things as birefringence and other properties of our medium. So little tricks in our microscopic systems here give us some extra information, encoded again in the spatial structure of light. Now, this is when light comes from an optical scene or is sent through an optical scene. What we can also do is we can choose to shape the light before it hits the optical scene. And this is what, for example, is done in STEP microscopy, which is stimulated emission depletion microscopy, one of the Nobel Prize awarded techniques. I think it was 2013 or something. So if we think about fluorescent microscopy, what we have usually fluorescent markers, and they give us some signal in confocal microscopy, which is limited by the diffraction limit. So we see some nice structures. However, the resolution is not as precise as we want them to be. So if we want to get better, what we can do is, after eliminating our samples with one specific shape of light, or we have then our standard point spread function of the optical system, we can use a ring-shaped intensity structure as it is shown here, and pretty much delete the outer wings of our original point spread function in green in the background, and get a new effective point spread function, which is much more narrow and gives images, let's say, beyond the diffraction limit. So we get new images with much higher spatial resolution. And this is enabled by these beams, which we see here. These beams do not only have this donut or ring-shaped intensity, if we look at them from the front, they also have this spatial variation in their phase. Here, blue to red goes from 0 to 2 pi. And these are so-called optical vortex beams. And this is one of the classes of beams which pretty much kicked off the big field of structured light fields, and are also called orbital angular momentum beams and so on. So in the following, I hope we're going to discuss a little bit more about optical vortex beams and what they are useful for. What are these beams actually, and how can we use them? We will look at one particular example where we recently worked on optical metrology in microfluidic channels. And then we will look at a second example where we look at polarization variations in light and nanophotonics and how we can use that in order to create what we call a vector beam decoder. And in the broader context, this device is used for quantum cryptography. So I try to give you a little bit of a feeling of how broad the field of structured light actually can span with the different abilities. So first, as I said, let's start with what we can call optical vortices in structured light. So if we talk about optical vortices, the first example we have already seen is this kind of light field. So always imagine that if we look at these different structures, the beam is propagating towards us. So we have the ring-shaped intensity or amplitude structure, and we have the according phase distribution going from 0 to 2 pi, from blue to red. So now these vortices here, or 0 to 2 pi turns, are called the topological charge, which goes once from 0 to 2 pi, but could also go twice, 3 times, and so on. And usually this is defined by this little factor we have up here, which is e to the IL phi, describing this phase distribution. So now why do we call this a vortex beam? Well, if we think about vortices, we might think about the vortex of water going down our sink, or we might think about material structures where we have these screw dislocations in our materials, like water creating a vortex around the dislocation. And in light, it looks very similar. So if we let this beam here propagate in space and draw the wavefronts, what we would see is this spiral forming, very similar to what we have in our material. And in the center of the spiral, we have a line forming. And along this line, or exactly in the center of the beam, what we have is a point of undefined phase. So we cannot say what phase value the light field has here. And this is actually an optical singularity. So this draws the connection to the field of singular optics. So any kind of singularities we can find in light, and they can behave pretty similar to what we find, for example, in material physics, where we have our singularities also going through the whole material from the beginning to the very end. And if they want to disappear, they pretty much need to propagate through the material and exit at the side. The same would apply for this singularity we have here. It's a stable thing which propagates in space and pretty much carries its surrounding. So it's like a skeleton, I would say, of structured light with the surrounding structure in phase. So now these beams are our optical vortex beams, but they are also called orbital angular momentum beams, so OAM beams, because they can carry orbital angular momentum. So that light carries momentum is nothing super new. If we think back at what Arpian and Kepler described in the 16th and 17th century, we had the sun pushing away the tail of a comet. So what we see here is the comet, and this is the long tail. And what they observed and described is that this tail is not flying behind the comet, as you might think. It's actually always pointing away from the sun. And this is due to the radiation pressure of light of the sun pushing away the little particles. So this was a very old concept, and much later, but actually Nobel Prize awarded, Arthur Ashkin described how we can use light to actually push particles. So he was showing that we have dielectric particles in a laser beam, and we can see that the gradient forces and the scattering forces of light push my particle in the propagation direction of light. So the second force, what is called the gradient force, actually pulls to areas of high intensity. And if we now decide to focus this light field, what happens is that we can find a point in space where we have an equilibrium between the gradient force and the scattering force, so that we can actually trap a particle in light. This is our optical tweezers, and this is a means which we can use to manipulate objects also in biological samples, use it for calibration measurements, and many more very fancy things. So if you're interested in that, there's a lot of very interesting reviews about optical trapping out there. So now what does this have to do with structured light? So if we have our optical trap, we can obviously move this object as we like if we move our laser beam. What we can also do is we can change the polarization of light, and if we have a shape which is not necessarily a spherical object, or we have a birefringent object, the polarization will actually cause our particle to spin according to its handedness, so right-handed or left-handed circular polarization. Another thing we can do is we can decide to change what we would call the trapping potential, so the light field we use for trapping. So let's say we use the beam we have seen here, which is our optical vortex beam, which has a ring-shaped intensity. As we learned, the particle will move to areas of high intensity, so it will be trapped in the ring itself. And now we additionally have this phase variation. And if we look at this structure of light, we can already imagine what might happen, because if I would draw the k vector, so the energy flow, on the wavefront we have here, it would point somewhat like these spiraling spaghettis. So depending on where I find my particle, it will be pushed in a different direction. It will always have a little bit of a vector pointing in the direction of my phase gradient. So what actually happens is that I can orbit particles as they are trapped in my little vortex beam here, so that I can make them move in my optical trap. So now this might make a little bit more sense if we think about what we call orbital angular momentum. So these beams, depending on how often I let them go from 0 to 2 pi, the spiral here becomes faster in its period, and I can make particles orbit a little faster. In the end, this can be related to the orbital angular momentum, which is given by how often do I go from 0 to 2 pi, so the topological charge, times h bar per photon. So I can make objects move. That's quite interesting, or just a very fascinating observation. Actually, it has also been used to do viscoelasticity measurements in media, where you can change this vorticity and look inside a cell, how viscoelastic is my medium. And by this, you can analyze things as cancerous cells and many other properties. So now here we already saw this topological chart from 0 to 2 pi, but we can actually go multiple times from 0 to 2 pi, either left-handed or we can go right-handed, which just changes the sign which we have for our topological chart. And whatever kind of light field I'm here creating actually can be described by a superposition of all these different L values. So I just give it a weighting factor, and then I use one of these beams here on the right to create my superposition. So this gives a lot of different fields I can form, but this is just one mode set which exists in structured light. There's also a lot of other fields which are also called scalar structured light fields. And this is a nice illustration we have for this. We can go from very random fields. In blue colors, we see the intensity structure, and in the background in grayish, we see the according phase. So even if I just have a random structure, which is created by scattering, this is actually also a structured light field. And in the back, we can see that there's a lot of different vortices in the transverse plane of the phase. I can also think about laser modes as Laguerre-Gaussian modes, or more elliptically shaped modes as Ince-Gaussian modes. These are also spatially structured light fields. They have been used in optical trapping, but also many other applications. It's also very interesting to think about fields which have some kind of periodicity in their transverse plane. These fields here, these two examples, are actually non-diffracting. This means that they are propagating in space and they are not changing their structure. They are not diverging or anything. And there are also light fields which can actually bend as they propagate, so-called Airy beams, which can be used to actually shoot particles around a curve. So I can use a lot of different light fields here for various different properties. And I can access them, for example, with a spatial light modulator. There are many other tools. This is just one device we can use, where our little screen we have here in the front can actually be used to change the amplitude and phase of light. So now if I can do that and have all these different fancy light fields, I have various different areas of application. We already talked about super resolution imaging, our step microscopy, where we used our simple, let's say, phase vortex beam. The same can be used to manipulate materials as we do in material machining. Here you can draw, for example, these nano needles by using the orbital angular momentum of light. The orbital angular momentum of light obviously was also used in optical trapping, but this is just, let's say, the easiest example of what we can do with structured light. There are many others, as for example, this optical snowblower. I always like this example in winter because it's very relatable to me nowadays. But this thing can actually blow particles from one compartment into another. And as you can see, this has been done quite a while ago, but is still a very highly appreciated paper. So now we're going to talk about what is shown here on the right, a field of optical metrology, where we can also use phase vortices to get some extra information. And what this little ambulance here in the top is indicating is one, let's say, effect we're going to take advantage of, which is the Doppler effect. And it's actually not the standard longitudinal Doppler effect we observe as we propagate with the light, but it's actually the so-called transverse or rotational Doppler effect. So if we talk about Doppler effect, we all know the sound an ambulance makes as it approaches and goes away from us, which shows a frequency shift, which is measurable, and by this allows tracking of objects which are moving towards us or away from us. If we now think about a flow of objects in, for example, a microfluidic channel, in any kind of turbulent atmosphere, and so on, there's also motion which is orthogonal to the beam propagation. And this is something we are interested in. So if we think about our optical vortex beam, we let it interact with these particles which are flowing in a certain direction. And the rotational Doppler effect actually describes that if we do that, we have the spatial phase structure and we have our transversely moving objects, we also get a frequency shift, which is dependent on the topological charge as well as the transverse velocity of our little particles. So let's think about this a little bit more in detail. If we think about the scattering these particles are causing, they actually cause the light to have some extra phase variations. And these phase variations are related to how the particle is moving in my beam. So if I think about my phase vortex structure here it's a different color map as you see here on the right. If I have a moving object in my beam, the phase structure is moving azimutally with the velocity, which is here the capital omega, and it's dependent on the time. So what happens is I get a phase term in my beam, which has some kind of frequency and the time dependency. So now how can I make this visible? Well, if I have my beam which interacted with a rotating object, I can have a reference beam interfering with it. And as we have a time oscillation here, we should see an oscillation in the interference pattern. This is something I can detect with the photodiode because this is going to be a very fast motion. And then I can translate this into some variations I had in my particles or my object which was rotating. So now if I want to have a stronger effect, what I can do is instead of using one beam orbiting in one specific direction, I can have two beams, one orbiting left-handed, one orbiting right-handed. If I do that, both of them will experience this Doppler shift. And then I interfere the two beams. And if I interfere two orbital angular momentum beams, what I get is some kind of this petal structure. So if you imagine I go around the optical axis from 0 to 2 pi, I do this left-handed in this beam and right-handed in this beam. Wherever the phase values obviously are getting a phase shift of pi, I get destructive interference, so the intensity disappears. So now if we have this oscillating in time, what happens is that this intensity dot I can observe with the photodiode is actually moving. So this is the motion I actually want to detect. I have an intensity which is dependent on the time as we have our variations of the object. So if I Fourier transform the whole thing, I get a frequency. And this frequency is the one which is related to our velocity and our topological charge. So this can be used to track the velocity of the object. So this is an interesting effect and is well known for quite a while, but usually it was just used to track velocity of some orbital motion of particles. So the particles here were tracer objects. Now we thought that this is a quite, let's say, a big potential which is not fully exploited because we only know that the velocity is dependent, is measurable with this rotational Doppler effect, but there are many more things we might want to investigate, and maybe the Doppler effect can show us more about this. And as I was collaborating with someone who works in microfluidics, this person was particularly interested in investigating droplets which are forming in the microfluidic channel, thinking about industrial applications where you might have liquid waste and small objects which are in the liquid waste and you would like to detect them. So we came up with a principle where we wanted to investigate, can we not only analyze the velocity of droplets in a microfluidic channel, but can we also analyze other microfluidic properties, especially if we have emulsions? Emulsions means we do not only have one droplet which is moving in the microfluidic channel, but we might have multiple droplets. They might have different sizes, they might have different densities, and so on. So we want to know what kind of properties in a microfluidic emulsion as the volume of the droplets, the density, the frequency, velocity, which of those are actually influencing the Doppler effect and which of those can I detect using the Doppler effect. To be able to do that, we had our first microfluidic chip. In this chip, we were combining oil and water in a so-called T-junction. This T-junction allows us to shape what kind of regime we want to be in, the so-called squeezing regime or jetting regime. Squeezing means that the droplets in the channels will be pretty much squeezed into the channel. If we have jetting, we have a lot of little droplets. This hugely influence how the droplets are moving through the channels, which is very interesting from a physics point of view, but it's also very important if you think about applications of any kind of fluidics. So now this channel here allows us to control this by changing the pump of our oil or of our water. Doing this, we then choose to use the emulsions we are creating and pump them into this circularly shaped channel. And this is our sample chamber where we send our light field through. So we have the circular motion of our droplets, and we send our topological charge, 1, -1, and so on, beams through this channel. What we actually see experimentally is shown here in this big picture, where we have our channel here in the background. We have all these different droplets. You see it's a huge amount of droplets, which are actually squeezing and moving as we pump through the system. And in the background, these bright areas we can see is actually the superposition of two beams which have opposite topological charge. The one is going right-handed, one is going left-handed. So we have constructive and destructive interference as we go. So now what we need to do is we need to control our pump. We are controlling the beams we are sending in. We can change the topological charge. All we can do purely digitally, because we have our computer control generator, we have our computer control of our fluidic system. And by this, we can then create our different signals changing in time and transform them into our frequency spectrum, the one where we should see the Doppler effect. So if we do that, what we get is various different signals. So the red one, the orange one, and so on are all for different topological charges. So we changed it. And as a little reminder, the Doppler frequency was dependent on the topological charge as well as the velocity. So if I increase the topological charge, this frequency peak we get from the Doppler effect should shift. This is the first observation which we just confirm as we do our measurements. If we increase our topological charge, the peak you can see here is shifting to the right. So this is the expectable effect. This is what we want to see. And from this peak, we can then calculate our velocity we want to have. Why is this interesting? You might, well, I think my first idea for microfluidics was, well, if I know how fast I'm pumping, I should know how fast the things are flowing here. But it's a huge difference to know how fast is your liquid versus how fast are your droplets. So the droplets in here are experiencing various different effects, for example, droplet-droplet interactions, but they are also touching the borders. Are they not touching the borders, which changes a lot if the whole liquid is flowing as one, or if the droplets are flowing at a different speed than the surrounding medium. So this measurement in the end gives us an idea about how are the droplets moving versus how is the liquid moving. So this was the first observation, which was very interesting to us, because usually if you want to know these things, what you would do is you would take multiple images as the video is moving forward, and then you track your little droplets. Obviously, for that, you would need a high-speed camera, or you would not have a very good temporal resolution. And as you can see here, if you have these dense amount of droplets, it's very hard to identify which droplet are you tracking as you go through the different images. So by shifting towards, I don't need to see anything, I just need my photodiode and I can measure the velocity, it's a huge step for microfluidics, because this enables a lot of different measurements at much higher speeds than it was originally possible. So now I said we have also these other properties of our emulsion, which are interesting. And that was the next thing we wanted to investigate. So what we changed next is first just the velocity of both of the liquids, so the oil and the water. And we observed the shift changing as it should, because if I increase the velocity, I should see that the frequency peaks are also moving. So this is what we observe in these two pictures. But what we can also see, if you look a little closer, we have here a full width half maximum of these peaks. And this is changing as we change different properties of our liquids. So what we, in the end, could identify is that this full width half maximum can be analyzed as we go through the different parameters of the beam. And you can find out that there's a very particular change in the full width half maximum, which lets you draw conclusions if you are in the jetting regime of the small droplets, or if you are in the squeezing regime with the very big droplets. And you can also identify what is the density of the droplets in my channel, and what is the three-dimensional distribution. So you get a lot more information out of the system by simply using the Doppler effect instead of trying to track your particles as you would usually do in image-based analysis procedures. So much about dry microfluidics and what optical vortex beams can do. But obviously, this is not all we can do with structured light. This is just one of the different applications we can. So far we were talking about what is called scalar structured light fields. So light fields which are varying in their amplitude and the phase of light. These were all the different beams we looked at, so various fancy structures we can use for different applications. But as I said, this was always limited to the amplitude of light and the phase of light. So now what we can additionally have is the polarization variation. So if we think back about the blue daylight sky, where we had the variations of the polarization of the sun, well, we can do the same intentionally in laser beams. So what we can get then is what is called vectorial light fields. In this case, the polarization of light is spatially varying. So in the equation here, you can still see the amplitude and the phase, but now we also have the polarization, so the oscillation direction of light, which is spatially varying. If you want to think about these things in terms of scalar light fields, well, you can say that I take two vortex beams here, so we can see the phase variations left and right-handed, and we have the polarization of one of the beams being right circularly polarized, the other one is left circularly polarized. Now, if you think about polarization, if I take two circular states and I superimpose them perfectly, I get a linear state of polarization. Dependent on the phase shift between these two circular states, I get different orientations of these linear states of polarization. So if I analyze the phase difference spatially between these two beams, what I get is spatial variations in polarization. So I translate my phase difference here into polarization structures. This is what you would call a radially polarized beam or a radial beam. But obviously, if I have all these different scalar fields, I can combine them in similar ways. I can get various different structured polarized beams. So what I have here is just some examples of these linearly polarized fields, what we can call flower structures or web structures because of the orientation of the linear states in space. But I can also get something which is called full Poincare beam. So people who work with polarization might know that the Poincare sphere is something we like to use to represent polarization on it. If I take all the states I can find on the Poincare sphere and put them in a beam in the transverse plane, I get what is called a full Poincare beam. So here the little ellipses indicate the elliptical state of polarization I have in space. Other things I can do well, I can take one of these fancy beams here and combine them and get things like in-Gaussian vector modes and many other fields. So first of all, these might just look interesting, but obviously they again have different features, different properties which are of interest. They also have singularities which are very interesting, which through space propagate, have behaviors as a skeleton and so on. So a lot of different applications. One thing I would like to point out is the focusing behavior of these fields. So if you think about microscopy, which we talked about earlier, what we usually do is we send light through an objective, and these beams with their structured in polarization become particularly interesting in this case. So why is that the case? If we think about polarization structures of light before we focus them, we can think of them in terms of radial components and azimuthal components. So radial components here in black, azimuthal ones in gray. If I send this through a lens, all components which were radially oriented, like black arrows, will be tilted pretty much, if I think very easily about this as in ray optics. And this tilt in the end causes a component which is pointing longitudinally in space. So I do no longer just have EX and EY components of polarization, but now I get EX components, Y and Z polarization components. So the so-called longitudinal polarization. Obviously, each ray we have here still has just transverse polarization. But in this focus, if I analyze it, I get EZ, EX, EY, and EZ components. So if I focus radial beams, I get very strong Z components because the tilt here is the strongest. If I have azimuthal components, as I can see here, the gray vectors, these are pretty much unaffected as I focus. So I get almost no components, or ideally no components at all which are contributing to the Z component. Now, knowing this, that radial components create strong Z, azimuthal components create almost no Z, what can I do with that? Well, I can use it to customize more light. And in this case, I can create light fields in this focus, which are structured in 3 different polarization contributions. And this was done extensively in the past and still is done a lot, because I can create, for example, very interesting flat top beams, bubble beams. I can create an optical needle where all the polarization is pointing in the propagation direction of light. And even more complex, I can create topological structures as an optical Möbius strip. Some of you might have seen this very nice paper, I think it was 2015, where each of these little lines here is actually a polarization state in space. So if I would take this little focus here, cut through it, and then trace the polarization along a ring, I get this kind of structure. So I can actually do some topological physics in the focus of light. This is not only interesting from a fundamental point of view. Again, we can find various different applications here. And one of the applications where focused light fields, non-Parkside light fields come in is nanophotonics. So if I think about this light field here again, this is actually very similar to what you get if you have one small Me resonator. So if I take a little particle here, which can be the cylindrically shaped resonator, and I decide to have an electrical dipole mode in the dielectric object, and I take a lens, what I will see is that this object gives me radial polarization. Again, if I look very closely, it would look pretty much like the radial beam here. So it has Ex, Ey, Ez components. And these structures here tell me what kind of mode do I have in my little particle. And the mode I'm having in this particle actually allows us to shape light even more extensively if we use nanophotonics. This brings us to what I called structured light meets nanophotonics, and in particular to meta surfaces. So if I have these little nanoresonators and I have the modes I can excite in these resonators, I can use the knowledge about these modes and what kind of light fields I'm actually creating pretty much in my resonator in order to shape light at a larger scale. So what I can do is I can use this little resonator as my meta atom. So it's pretty much my little building block in order to create a whole surface of building blocks, and all of them together support different modes, electric and magnetic modes in case we use dielectric objects. And we can use the size, shape, orientation, spacing, and so on of all these different resonators in order to shape the flow of light. So what that means is if I arrange them in a specific manner, what I can achieve is I can change the shape of light as they go through the resonators. For example, I can create a meta lens, in this case, as it is shown here. It focuses light into a spot. Nice feature. The cool thing is this little meta surface is obviously much thinner than a traditional lens, just a few 100 nanometers. So this allows us to get very thin optics. Also, using these different shapes we can have of resonators, we can also have extra functionalities. In this case, we translate our Gaussian beam, for example, in a vector beam where we have orbiting of our transverse phase structure for different polarizations. Or I can even create something much more complex and say that, hey, I want my red color of light be shaped into this knot intensity structure. My blue one should have this one, green, this structure, and so on. So I can do color dependent encoding into my meta surface, also polarization dependent, and so on. So it's like a big advantage, and everything is stuffed into a very thin layer of nano objects. So now what do we want to do with it? Our goal was to create a device which actually implements the meta surface idea, but we didn't want to have a device which is working in free space. We wanted to have something which is working integrated. Integrated means that we imagine we have a waveguide, and this waveguide is coupling to a meta surface. This is a paper from the ALU group, where they used, as in this example, a meta surface on the waveguide or a meta surface implemented into the waveguide in order to shape light. Based on this idea, you can do various different things. They have shown, for example, that you can create a vortex beam after propagating through the waveguide. You will have the emission of a vortex beam. Or if you go through the waveguide and have a different structure, you can actually also shape some of these so-called full Poincare beams and so on. So it has all the same tools we have in traditional metasurfaces, but we implement it into a waveguide. Why would we do that? Well, if we think about devices and how we want to use light on a chip, this has the advantage of coupling free space optics into a device using structured. So if we have everything afterwards on our little chip, we can do photonic post-processing on the chip. And this was our idea when we designed our device, which was supposed to be used for quantum key distribution. We said in the beginning, we want to get to, say, a very different example of how we can use structured light, which is quantum cryptography. The idea here was that, well, or in general, is that you usually have Alice and you have Bob, and Alice and Bob want to communicate securely as they live in the quantum world, while we have Eve coming in from the side, and she wants to have all the information she can get from the communication of Alice and Bob. So if they want to stay safe, they have to use something which is secure. And what you can do, one thing you can do is you can create a cryptographic key using quantum mechanics. In this case, the quantum part of the idea is stuffed into the generation of a key, and then you can use this cryptographic key for classical communication. So how can we do that? We can use structured light. Well, Dana, I told this in the beginning, but the idea here is that instead of using, for example, two orthogonal states of polarization to send a 0 and a 1, I can use the spatial structure of light to also send 0s and 1. Why would I not use polarization, for example? Because horizontal and vertical could be a 0 and a 1, and I can perfectly create this with single photons and so on. If I use structured light, the nice thing is there's not only a 0 and a 1 I can send. So I do not only have a binary system. I can actually send multiple binary numbers or higher numbers than 0 and 1 with one structure of light. So what we usually need is we need orthogonal states as our horizontal and vertical state of polarization, which were used to send a 0 or a 1. So if we look at the modes we see here on the left, each of them is orthogonal to the next one because of the polarization structure they are having. So if I multiply the function for this beam by this beam, I get a 0. This means that each of these beams can correspond to a different number. So if this would be 0, the next one would be 1, I would be out of numbers. I could call this 2 and the next one 3, or I call it 0, 0, 0, 1, 1, 0, 1, 1. This is one mode set I can use to send these numbers. And there are other mode sets which I can use to send these numbers. For example, if I change the phase structure of light additionally, I can use diagonal states and anti-diagonal states with different phase structures. And again, all the modes are orthogonal to one another, so they can send the same binary sequence I showed here. So now why do I need two? If I do quantum key distribution, dependent on the protocol you use, you need two bases. So in this case, this is basis psi, this is basis phi, and I'm not going to bore you about all the fundamental details. Our goal was we need these 8 modes, and if we have these 8 modes, I can send the information of the key from Alice to Bob, and then use the key to be secure so that Eve can't get any information. The important part is that all the states are orthogonal to one another, and we have a relationship between the bases phi and psi, and the relationship is shown down here in this equation. In principle, each of the states we have in phi is described by a superposition of all psi states. And there's a specific relationship we need to have. If this is given, we have so-called mutually unbiased basis states, and this allows us to use the BB84 protocol, which is one protocol to create a cryptographic key. So now, boring you with all these quantum mechanics stuff, now let's go back to photonics. What does this have to do with our chips and our metasurfaces? Well, we want to do the whole thing on a chip. It is known that these beams can be used to generate a cryptographic key, but usually if you want to generate these beams, you need bulky devices like a spatial light modulator, different wave plates, and so on. So a lot of free space optics in order to create these modes. Now, our idea was we want to have the whole device on one chip so that Alice and Bob each get a chip, and we measure and decode, encode and decode in these modes we can see here. So the device need to be able to identify each of these modes individually. To do that, we use inverse design. The idea was that this little device here in the center is an inverse design meta-surface coupler. And we have 4 waveguides coming out of that, corresponding to 4 orthogonal modes. And then if we can get 4 of them, the other 4 are described by a superposition of the first 4. So if I look at my device, we started with, let's say, a circular area, used our photonic optimization, assuming that we want to get these 4 modes here on the right. So we wanted to have a vortex mode with diagonal or anti-diagonal polarization. If we do this little trick with a little bit of computation, you get this beautiful structure nobody would have thought of by themselves, but our computers are clever, our codes are good, and this is what you get out. So just to give you an idea about the dimensions, the whole thing is 3 times 3 micrometers, so very small. And the smallest feature size we have in this device is around 50 to 80 nanometers, so very, very small. We don't go any smaller because then the whole thing is pretty much impossible to fabricate. The whole device is made from silicon and insulator. And the waveguides in the end carry the mode, which is shown here in this little cross section. So all of these waveguides now go into these couplers we can see here. They are combined with different phase shifts so that in the end, if I can create these 4, I can also create the other 4 because I know this equation here. So now what do the modes actually look like we achieve with this inverse design structure? The structures we get for our 4 orthogonal modes are shown here. So if I imagine I go in with waveguide A, B, C, and D, I get A, B, C, and D as the modes we get. So what we see is the intensity in the background, polarization on top, and here we see the phase structure. As a side note, this might look like this experimental results. These are the results you get from numerical calculations. They might not look ideal, but actually this is exactly what we want to have, because the most important part for our optimization was that the phase has the vortex we can see here, and this is what we actually got. So the phase is exactly as we like it. The intensity is not as important. Now from these 4 modes, you can actually get these other structures for the polarization structured beams. This is the Stokes parameters. We're not going to look in those in detail. You can see the same information if you look at the little polarization ellipses here on top of the intensity, and you can see that we have some kind of a radial orientation, azimuthal orientation, and some kind of hybrid polarization. So now if I have all these beams, I should be able to do quantum cryptography. But first of all, we need to prove that experimentally the whole thing is doing what it is supposed to do. So what we did next is we optically fabricated the device. So what you see here in the very center is our little inverse design coupler, so our meta-surface coupler. And it's going into 4 different waveguides, and they end at 4 different outputs. We were simplifying the whole thing because if you imagine creating the whole chip at once, you don't know where your mistake is laying. So we started with, we need to prove that this inverse design structure is doing what it is supposed to do. So what we do to prove that, we generate our modes here on the right with a different optical system, and then we focus them onto our little chip, and we analyze which of the waveguides are actually lighting up. If I'd send in one of the scalar modes, so the phase structured beams, only one of the waveguides should light up because the inverse design was made to answer to one of the beams in each of the waveguides. If I send in one of the vector modes, all of the waveguides should light up because according to the equation we saw before, each of these modes is described by a superposition of all of these 4 modes. So if we do this experimentally, this is exactly what we see. So if we send in a scalar mode, which were our phi modes, I see one of the 4 waveguides lighting up. If I send in one of the psi modes, all of the waveguides are lighting up. So if you show this in a whole matrix, assuming that we measure our 4 outputs here, sent in a vector mode, all waveguides light up, sent in a scalar mode, only one of the waveguides is lighting up. So this matrix in the end is proving that experimentally this device is doing exactly what it is supposed to do, so that Alice and Bob in the end would be able to create their key. And with this, not boring you any longer about quantum mechanics or quantum cryptography and many more things, just a little picture summary of what we discussed about. We talked about how we can use vortex beam for microfluidic measurements of emulsions and how the focusing behavior of structured light is actually shaping some nanophotonic similarities, which we can then use in order to create our photonic chip, which is then used or enabling the communication of Alice and Bob by creating a cryptographic key based on structured light. And with this, I thank you for your attention late this night, and I hope the janitor didn't enter yet and throw you all out.
Thank you so much. So as long as you have a few more minutes for some questions, I think we've got about 10 minutes on this side. So would like to kick us off? I actually have a question about the optical vortex beams. I've worked with optical vortex beams for astronomy applications where we try to create a dark hole for high contrast imaging. Are there similar problems in biological imaging with sort of trying to have high contrast imaging, or is it exclusively used for what you've presented?
So it's also used to pretty much do edge enhancement in imaging, which is very useful. People also now created meta surfaces which do the trick. The nice thing is that knowing that vortex beam can do things like edge enhancement in imaging of biological samples, if you have a meta surface which is able to do that, you can slide it into your system, have contrast imaging, slide it back out, and you have normal imaging again. So very similar to what we now use for polarized light microscopy, or these microscope having the little slot for the polarizer. So the same trick can now be done by using, say, a vortex encoding metasurface. So there you use the vortex beam for imaging, contrast imaging in biological samples, which is kind of cool. I like the idea of having a lot of different metasurfaces just being slid into the microscope, and then you can see a lot of new features.
Thank you.
I've got a question about the structured light, but I'll ask it in the context of the quantum cryptography. When they tried to encode ones and zeros with polarization, they found that since they want to go long distances, fibers are very sensitive, at least the polarization fibers, to environmental issues. So in the structured light, how sensitive are they to the environmental issues through long distance fibers?
Extremely good question. So people tried to do two different things. They tried fiber communication with spatial modes, and they also did free space communication over long distances with spatial modes. One thing in fibers, you can have fibers which are particularly designed to carry spatial modes, so they can be relatively stable. One major issue is that, again, if you have polarization sensitivity, the polarization structured fields obviously split up equally and change equally as horizontal and vertical states would do. So a lot of people, and this is why our device works at this intersection of free space and on a chip, a lot of people tend to go into free space once they use spatial structures of light. So I said at some point that these singularities are some kind of a skeleton of structured light. The nice thing is, if you have, for example, a vortex beam going through free space, it's going to change the spatial phase distribution. But what stays is the phase vortex in the center. So, and this phase vortex in the end describes how often do I go from 0 to 2 pi, which is the crucial information for carrying this information, or crucial, information to information. Well, so in the end, if you get the phase vortex transmitted, the singularity, you have all the information you need, but it highly depends on how strong your turbulence is. So people have investigated, is it better to have phase vortices versus, for example, Hermite Gaussian modes, where you just have two intensity spots up and down and on the sides. It seems, for example, that these Hermite Gaussian modes are more stable in high turbulence, whereas if you purely use communication based on singularities and topological constructs, you can also achieve high stability if you don't take the spatial structure into account, but only the singularity. So there was a recent paper from Andrew Forbes' group in South Africa and also from Natalia Lukushiva at Duke. And both were discussing using what they call skirmions and Hopfians in light. So it's like creating cool mathematical constructs in light. And it's again dependent on the spatial structure. But this topological structure is stable in turbulence or can be made stable in turbulence. So this is still at the beginning of the investigation. I think this is the better pathway, or you need to have fibers which highly support spatial modes. But also people do research on that. I think it's still promising, but it's much more complicated.
Thank you.
Sorry for the very long answer. There's too much to do research on, I guess.
We recently actually had a talk about the design of those fibers that can take things. Dennis Shepard's talk.
Nice.
It's on YouTube on our channel. So, all right. Next question. No. All right. Yep.
I don't know if this question makes some sense, but I'll try anyway. So with the boring lens, familiar with the Rayleigh criterion for resolution? Is there any analogous sense for these sorts of beams for resolution? I'm just racking my brain thinking, and what got me thinking about that was how when I'm aligning a system, assuming a Airy function, the convergence is nice. And talking about generating these things and the discretization of such things, and it's less straightforward to me. So
yes, so I think
sorry for the hairy question, I guess.
No, it's a good question. I think if you think about the big field of point spread function engineering, this is a little bit what I often think about if I think about sending structured light into a system to get better resolution. Because in the end, I put a modulator for light into my imaging system, which becomes part of the imaging system, right? So what I effectively do is I change the point spread function of the system. And as we know from, for example, the work of W.E. Myrna, if I change the point spread function in a clever way, I can get extra information as, for example, the nanoscale resolution in Z distance with this double helix function he was using. So this is done by adding a spatial light modulator and a phase function, which in the end means if I send light the other way around, I would send different illumination into the system. So this means that the spatial resolution of the microscope didn't change. It still all applies to the standard limit which I can achieve according to the wavelengths of light. What I changed is I encoded information which is at the nanoscale or at very small scales into a feature of light which I can then analyze. For example, if I think about my single molecule, if I just look at it with my standard imaging system, it's always going to be a blurry spot. The blurry spot is going to have the same size if I always use the same microscope, but dependent on orientation, it's going to be more blurry in one direction than the other. Right. If I instead analyze the polarization of the emission I get from my single molecule, and for example, use a radial polarizer, I will get the information of the orientation. So then I get some nanoscale features out of my molecule, which I can use to correct the image I had. So this is again some work from Myrna, but also from some people at University of Washington, St. Louis, where they pretty much post-correct the image from the polarization information you can get. So in the end, the information is there. It's still encoded in my standard blurry spot I had, but by using some tricks, I can analyze the spatial structure which came from the source. And by that, I can correct the image and tell you more about not only the orientation, but the precise three-dimensional position of the emitter and create an image which goes beyond the diffraction limit. So still, all the standard rules of imaging apply. I just use some tricks to get some extra information out. If that answers the Harry question, or just gave you more to think about, which is also not the worst, I guess. But so if you have more ideas, let me know. We did some nice work at Stanford also with W.E. Myrna, where we pretty much use metal surfaces and the spatial structure of light to get three-dimensional orientational imaging of molecules. So it is possible, but it's all somewhat, you get more spatial structure and more information. You don't directly see the molecule in a smaller spot. You just get a different image, and this image is carrying information.
Yeah,
Sure.
Eileen, we heard a talk at the Photonic Center recently about someone doing very high order OAMs, like 37th order.
Yes. Yeah.
Difference in the technique that you're using for the quantum key encryption. You were using the low order
Yes.
beams. Is there any reason to think that that can be extended to these very high orders so that
Yeah.
you could get 10, 20 bits at a time?
Yeah. Another good question. We did that in South Africa, not on a chip though. We did Bessel beams, so the non-diffracting beams, which also gives us the nice feature of what people like to call self-healing. So if you put some obstructions, the beam is still there. It doesn't really reconstruct. People like to call it reconstruction. It just looks the same after a certain distance. And we use charges up to plus and minus 20, which is not 200. But if you think about it, if you go from plus 20 to minus 20, you have like 41 bits, which is great. It gives you a huge matrix for measurement. And the nice thing is, even though I must be honest, the beams look shitty because you go to so high charges, you lose a lot of energy. And also, if you think about the spatial light modulator, it has just a certain number of pixels. So it's limited in its resolution. If I try to go to 20, I have less pixels to resolve the 20 in the charge. The beams didn't look nice. Free space propagation gave it some proper shape. But because I go to so high charges, the noise I receive in the matrix didn't matter anymore. So you get matrices where you got a very clear diagonal, which is the most important part. You still got a lot of crosstalk, but it still worked. It was a one-day measurement we did, and I did it like in a day for fun. And it gave you quite surprisingly good values without any correction. So this, in principle, showed us that we can do a lot of high charges. It's going to improve the noise ratio. So it's going to give us good signals. The main issue is once you generate them, you lose a lot of energy and you have to stay in free space. If you think about fibers, which are supposed to support like a charge of 20, I'm pointing a little bit too large. It's not going to be a gigantic fiber, but it's going to have more crosstalk. It's going to have more coupling into different modes as it propagates and so on. So this is only pretty much possible in free space, I would say. If you would go on the chip like we did, think about the inverse design area, you would need to increase it in size. That's possible. One reason we stayed small is these devices we created actually support non-paraxial fields, so focused fields, which are often used once you try to get into a chip for coupling. If you design larger devices, fabrication technologies are expensive and it takes ages to create these things. So if you have a small coupling area, that's cost effective, I would say. And at the moment, for our proof of concept of doing what we did, this is still sufficient. Obviously, if you want to go to higher charges, you would also need more waveguides coming out of the system. So let's say you don't just need 4, but you might need, in the case of 20 to minus 20, you would need 40 outputs, which is a little bit difficult if you think about that. But yeah, it's interesting to think of these things. I let someone else do that though, because I don't want to fabricate a device with so many outputs.
I think we have time on our side for one more.
Hi, that was an awesome talk.
Thank you.
In the microfluidics and its application in biologics processing, would you be
Nice.
able to, like, I'm trying to figure out how to ask this. If there was like maybe another oil, maybe your oil, or maybe some sort of like solid suspended, would you be able to tell the difference between that and the oil, between the water?
Good question. Yeah.
How many more things can we shove in there?
That's a good question. I honestly don't know because people didn't try it yet. So that's the nice thing. In the Doppler effect, people were mainly surprised you can measure velocity because Doppler was used for that, right? The longitudinal Doppler, people wanted to know that something is coming for them, but they didn't want to know what is coming for them yet. So now we know that we can not only measure velocity in the transverse motion of droplets, we can actually get information about like many more things. We didn't try more parameters yet because there was already a lot of parameters. I think the next step is, among others, what happens if we choose different components which flow through the system? So not only oil, but something which is something you didn't want in there, right? Let it be a bacteria swimming through there. Is the signal different? We also thought about they are small liquid crystals which you can stir it, and they would change polarization, which is kind of cool to think about because at the moment we were only using the phase of light. What happens if you also have polarization effects? So I think there's much more we could do. We just need to do it, but we didn't try it yet. So it would be very interesting to see what happens if we choose different media, I would say. And we need some modeling. So it's a complex system, as you can imagine, and it's only oil and water. But because of the shape of the droplets and not only the optical effects, but the microfluidic effects, like droplet interactions, effects on the walls, and so on, it's quite complex to model the whole concept we have here. So once we have a model, probably we can do even more. Or we just need to try what happens experimentally. That's another solution. I like to do that too, but then you're a little bit walking in the blind and you need to hope to find the light switch. So let's see if we try that.
Well, thank you very much once again.
Sure.
And have fun at Photonics West. All right.
Thank you.
So much.
Thank you.
Have a nice night. Bye.